Hi ladies and gents. So I wanted to share with you a quick little insight into you know a, an experiment which you can do at your own home, but also happens to be one of the number one mass producers of atmospheric gases on this planet, and is one of the main reasons why we have such a breathable atmosphere, aside from things like cyanobacteria and plant matter and whatnot. Now, understand that this is something that is a process that would normally take eons to do it on a planetary scale. But on something that is as minute as, say, a Mars hab or a desert property here on Earth, this can work right in your own backyard, and at the same time, it's an amazing way that you can produce atmospheric gases from nothing more than just water and a few other sundries, but we'll get into that. Now, for this to work, you do need to have a certain type of rocks, mineral to contain solar radiation in order for that solar radiation to then be manipulated into muonic and gluonic and neutronic emission in order to split water. Now, why would you want to split the water? Well, because we have two things that make up water, and it's almost in a breathable formulation, which when we add just a few other sundries to this, it becomes the basis for life on Earth. Well, the basis for breathable atmosphere on Earth. We'll get into that. First things first, I want to show you this. This is my favorite little friend right here. This is a bucket of, you probably can hear it, that sounds like gravel. Well, you're right. That is gravel. But it's a lot more than just gravel. There are things in this gravel which add to the atmospheric relative gases which we breathe in. These are organics, and you need to have those organics in order for this particular fissile reactor to work. And it is a fissile reactor, okay? It is nuclear reaction. So here we have some organics. Now that's just basic pieces of wood, right? And maybe some bark or something from a tree. We've got leaves. So, just your basic detritus materials which any property is going to have when you have human habitation. It's just kind of a given. You've got lots of rocks because the Earth is made up of rocks and dust. And you've got lots of this igneous rock like granite. This right here is the number one source for your nuclear reaction. Okay, now understand, granite on its own, it's just a whatever kind of rock. It's medium to somewhat more hard on the Holmes hardness. I mean, the help me out, whatever hardness scale you want. This is on the slightly harder side of that scale. It's still softer than diamonds, but it's a hard rock. Now, as you can see, the little striations in here are iron and quartz and little bits of radioactive materials and whatnot that are captured in this rock when it came out of a volcano. So we have that, okay? We have a semi-radioactive rock. Now, yes, of course, this is on a level which no nuclear reactor that provides power, say electrical power, would actually be able to run on. This could never power one of our super duper, whatever kind of fissile reactors that use water, steam, to drive a turbine. Okay, this will never do that. It doesn't have that physical capability. But what it does have is enough thermal retention in order to start a reaction within the inside of this rock. Okay? And that reaction lets off neutrons, it lets off muons, it lets off gluons and neutrinos. And these rocks right here are going to be the mainstay of your nuclear atmospheric power plant, because some of the, or actually most of the gases that are off-let come from this rock. We've got some other rocks in here, you know, your shale granites, common lava rocks, you know, that kind of same basic principle. Got your schist, you know, basically a conglomeration of gravel, and it's readily available. So let's take a look at how this works. Now, as you can see from my little diagram here, which is I did up on a piece of paper. Hang on, I gotta take my sunglasses off to see this. As you can see on this little diagram I made here on this piece of paper, we've got our gravel across the bottom. There's me right there, and a water hose, and you've got your descriptions and whatnot, because I did do this earlier. I went and wrote down all of this stuff so that I'd have it all present, all right? So here's your granite rock, the one that I was talking about, basically. Your chunk of granite, okay? There's your chunk of granite. So then we've got the sun right here, okay? And this is how this all works. So take a good look at it. Go ahead and pause the video if you want. You know, take your time, read it, understand it, and know what I'm talking about with the different work here. Disregard the coffee stain, okay? That's just a coffee stain. The rest of this is how this reaction takes place. You've got to have the water because it is a neutron moderator, so that when the neutrons bombard other granite, they release heat, not radioactive energies, okay? And as you can see here, when the solar radiation, photonic and otherwise, meets the top surface of this rock, where there is water in contact with it, it moderates the reaction and produces muons, gluons, and other particulates. Now when these go down and into other rocks, these heat up the other rocks and therefore give off ultraviolet and ultra red and ultra blue radiations, and these then feed into the rocks themselves, and that continues the reaction, okay? So by doing all of this reaction, what happens is that the water itself starts splitting its atoms, or the water itself actually starts splitting down, breaking down into hydrogen and oxygen. While that is happening, your rocks, your granite, is breaking down and producing radon and argon and neon and helium and xenon and just all sorts of different types of atmospheric gases that you would normally see, but just in such small profusion. And here's the reason why the ratios are what they are. Because granite is at a certain hardness, it breaks down slower. But because water is a liquid at room temperatures, it breaks down incredibly quickly due to this thermal reaction. So now let me run this through to you. I wrote down on the back end of this a particular little script, and here you go. Okay? Nuclear energy can be harnessed via granite-based gravel, water, and solar output to generate atmospheric gases and water vapor. This happens on a planetary scale, but it can be manipulated to both cool and create breathable atmosphere for desert properties, HABs, and etc. Now I wanted to add this little bit in there because a lot of folks have said, you don't know what you're talking about, Blaine, you're an idiot. You don't have any kind of training, any formal schooling whatsoever in this field. How could you possibly understand nuclear physics? So I'm going to tell you right now, I bet you didn't think I knew nuclear physics, did you? Bet you didn't think I taught myself that, did you? Boy, were you wrong. Well, let me put this forth out to you, because I put a lot of years and a lot of time into this. No, there is no safe nuclear reaction, okay? The rads will overwhelm your body every time. It doesn't matter how you do it. It doesn't matter how long you're exposed to it. You're going to expose yourself to some of this nuclear radiation, and it is going to do damage to your body. Now, you can lessen the effect by spending the least amount of time in that area or shielding yourself from that said nuclear radiation. But you are going to perceive some radiation. It's going to happen. You cannot walk outside into the sunlight without perceiving some radiation. Your eyes work from that. Your skin can tell what the different spectrums that your eyes can't see are doing, okay? There is no technology out there that is as sensitive to as many spectrums of electromagnetic radiation as the human body. Now you say, oh, well, we can't detect things like radio waves. Yes, you can. Yes, we can. I detect radio waves every time I walk outside. If you've got an implant of some sort, or you have some form of metal in your body, if your fillings are the old mercury, mercury lead type, or the mercury, not the mercury, the platinum enamel type fillings in your teeth. If you wear earrings, if you wear a tongue ring, if you have any kind of piercings on your body, if you have shrapnel in your body, these little tiny pieces of metal can perceive that. But I want to bring you in on something a little bit less well known about the human body that every other animal on Earth has more of. Even though we do have it, we say we don't, okay? They only have more of it. Doesn't mean that we don't have it. It just means that it's hard for us to find it in the human brain. And that is magnetite spheroids. They happen to be inside your brain. There's a lot of them. And they're in a spheroid shape because your body made it that way, so that it wouldn't damage the body if it moves around in its turn. It's a spheroid, all right? It's not exactly a sphere, but it's not a rhomboid, okay? And it's not, what was I calling that? It's not a rotundoid. And that's exactly what that is. It's actually what it's called. It's a rotundoid. It's a polygonal shape with two curved sides and two points, all intersecting. It's basically an ellipsis, but reversed. See, an ellipsis is like this. It's got the two curved lines, but they never actually completely intersect to create angles. Okay? This is your rotundoid. So, rotundoids, sometimes you might find a couple in brains, but they're not very often. You're more likely to find spheroids, which are imperfect spheres. And when they turn or move, your brain can perceive that because it has little receptors next to it that touch, just like on the ends of your fingers, okay? But these are in your brain. And this can help you to understand magnetics. It's a very convoluted, not something I can entirely get into because it is biology. It's difficult to explain with the amount of knowledge that I have because I've got too much. I understand it in its most infinite forms, and it's hard for me to relate it to other people because I can't. I'm eloquent enough, but I don't have the vocabulary at my disposal at this instance to be able to relate it to those who are less than understanding in those fields. So we'll not go there, okay? All I'm going to say is that by doing this simple process, okay, and that's, I'll show you in a second what that really is. It's just simply you spray water on a gravel driveway. What do you know? It does. It releases atmospheric gases, and it drops the temperature of the area, okay? And both of these effects are necessary when it comes down to keeping a moderate level of heat production and a proper atmosphere around your person, around your property, around your hab, whatever. Because consider this, I expect that somebody at some point in time is going to be taking this video and going to Mars and using it in order to create gases so that you can breathe. And Mars has granite on it. It's just not something that's at the surface, so we would actually have to dig for it, mine for it, and that would make it very difficult until the point where we can get to said granite, because granite is an igneous rock. It has to be created through volcanic processes. And for that to happen, there has to be a certain profusion of radioactive substances. There has to be a certain amount of geologic processes. And these have to come together correctly in order to create the rock. So when those crystalline structures inside of those rocks are formed and they become porous like granite is, it can take on things like water and then cause this reaction. Now, if you're wondering whether or not I'm basing this on something, I am. This is coming from the same ideas that are powering the Oklo reactor in Africa. Okay? That is a natural geologic nuclear reaction. It is happening within the Earth right now as we speak. It is going on and it is not stopping, okay? It's not something you can just stop doing. It happens. It's going on. Now, there is a lot of granite. There is a lot of uranium. There is a lot of other substances which are radioactive. Radium, radon, argon, xenon. They have radioactive isotopes, so when these come off, they're still radioactive, and they're doing all sorts of fun shit. Anyways, long story short, these reactions are what I am basing my findings in my research off of, for you to understand how this reactor works. So let's go take a look at the nuclear reactor. All right.